Artificial intelligence is frequently framed as weightless code floating in a cloud, yet it remains a massive, heavy, physical hardware undertaking. Standard enterprise IT infrastructure is designed to manage predictable, sequential tasks. When these legacy systems are forced to handle the millions of concurrent mathematical operations required for AI, the network switches and standard processors inevitably bottleneck and crash. This happens because AI workloads are not monolithic. They function in three distinct intensive phases. First is training, which requires massive parallel compute to build models from scratch. Next is fine-tuning, demanding rapid storage to compute iteration to adapt a model to specific data. Finally, there is inferencing, the live production phase where the model must deliver a response with near zero latency. Off-the-shelf servers cannot support these extremes. To scale AI effectively, an enterprise requires a specialized AI stack, engineered from the silicon up, to handle continuous, high-volume data throughput. Without this underlying physical architecture, even sophisticated open-weight models like Treecapital's Anven cannot operate efficiently. The hardware is the necessary foundation that allows the software to function securely and at scale. The foundational layer of the stack is the compute layer. General-purpose CPUs handle basic system orchestration, while machine learning is offloaded to specialized accelerators. These chips serve different roles. We use graphics processing units, or GPUs, for the parallel intensity of model training. For high-scale inferencing, we shift to neural processing units and custom ASICs, designed to execute specific AI tasks with maximum efficiency and lower power consumption. These specialized chips gain their performance advantage through low-precision math. By calculating using compressed numerical formats like INT4 or FP8, the processors can handle significantly more data without losing practical accuracy. Treecapital applies this principle to their Anven 3B models. Through 4-bit quantization, memory overhead is reduced, allowing it to perform high-level reasoning without the power-hungry infrastructure required by uncompressed weights. This schematic shows how that quantization enables edge deployment. By using the PyTorch execute torch runtime, these lightweight models can move from the data center directly onto microcontrollers and mobile chips for local inference. Specialized compute paired with mathematical quantization makes enterprise AI financially and physically viable. It allows powerful reasoning engines to run on localized hardware instead of massive centralized server farms. Even the fastest GPU accelerator sits idle if starved for data. The network fabric serves as the circulatory system of the AI stack, and any delay here creates a costly bottleneck. To keep the compute layer fully saturated, the network needs a non-blocking fabric operating at 100 gigabits per second or faster. This ensures that data moves between storage and processors without interruption. A smart storage pipeline feeds the network. The cold tier handles long-term archives. The warm tier stores active data for rapid iteration during fine-tuning. The hot tier uses NVMe flash to instantly feed datasets to the processors for real-time inferencing. As this diagram illustrates, the hot tier connects directly to retrieval-augmented generation pipelines. This allows the Anven model to instantly pull facts from an internal vector DB, grounding its answers in specific enterprise data to eliminate hallucinations. Zero-copy, perfectly tiered data pipelines ensure that inference is never delayed by storage latency. This architecture allows information to reach the processors at the hardware's maximum physical throughput. Once the hardware is optimized and data is flowing, the system requires a software orchestration layer. This layer governs the massive volume of data and compute power below it. This schematic shows how LangChain acts as the nervous system for the stack. It bridges the central Anven model with peripheral modules for memory and RAG, allowing it to function as a unified reasoning engine. Machine learning operations, or MLOps, ensures these connections remain secure. It monitors operational endpoints and provides the governance required to direct autonomous AI agents safely. Brakes are installed on high-performance vehicles so the driver can maintain control at extreme speeds. In the AI stack, strict governance and security measures serve the same purpose. They provide the necessary guardrails to accelerate enterprise adoption with total confidence. MLOps and orchestration turn a chaotic hardware stack into a reliable enterprise tool. They transform raw processing power into a predictable, manageable application layer. True AI readiness in the modern enterprise requires the simultaneous alignment of optimized accelerators, tiered data pipelines, and rigorous MLOps. Mastering this infrastructure leads to sovereign AI. As this complete architectural diagram shows, the enterprise owns every pillar of the stack, from the quantized models at the base to the private cloud and orchestration layers above. Running Anven on an air-gapped private cloud eliminates the security risks of third-party APIs and prevents vendor lock-in. By utilizing efficient 4-bit models on spot instance servers, organizations can reduce their inference costs by up to 90%. An AI application is only as powerful as the physical infrastructure it stands on. Mastering the stack is how an enterprise transforms its proprietary data into a secure, private engine of intelligence.